So, good afternoon, everyone. Welcome to Design for Additive Manufacturing session number 1. My name is Tino Stanković. I'm a senior scientist at Engineering Design and Computing Laboratory at ETH Zurich in Switzerland, and I will be your session chair for this session today. So we have 5 interesting papers, and yeah, we had an agreement that I just introduce quickly the presenters before we roll the presentations, because it's a bit easier to do it that way. And so let's start. So the paper number 1 is presented by Alan Eyre, who is a PhD researcher in additive manufacturing at the University of Strathclyde, Department of Design, Manufacturing, Engineering and Management. His research focus is in design innovation, lightweighting, design for additive manufacturing, anisotropy, and compliant mechanism. And he is going to present the paper on deformation taxonomy of additively manufactured lattice structures. The paper number 2 is presented by Fiona Schulte. She's coming from Technical University of Darmstadt. She's a PhD student there, I believe. And her research topic is in the field of purposeful design of additively manufactured mesostructures. And she's going to present the paper on influences and effects on scaling the pressure stiffness of additively manufactured mesostructures. The work number 3 is presented by, I can say, Didun. I think you wrote it like this in your CV, right? So Didunoluwa, he is from Wales in the UK. He's currently a PhD student in the design qualification of additive manufacturing for space applications at Luleå University of Technology in Sweden. And recently he also won a Best Poster Award for Surface Roughness Consideration Design for Additive Manufacturing at Swedish Arena for AM of Metals Academic Conference in this year. So I think this paper is then the follow-up, which will be exciting to see. He's going to present Surface Roughness and Design for Additive Manufacturing, a Design Artefact Investigation. Presenter number 4 is Jože, who is a senior lecturer at Product Development Division of the University of Lund. He has, in Sweden, he has extensive industrial experience and is a lecturer, or was a lecturer, or currently is a lecturer in the fields of design methodology, engineering design techniques, engineering design for non-metallic materials, and technical information systems. His current research topics are designing smart cyber-physical systems, design for AM, data mining and big data analysis, and application of agility methods and knowledge management in product development processes. And he's going to present the work on compounding composites from raw materials with extrusion directly on 3D printer. And finally, presenter number 5 is Alexander Zeidler. He's research assistant at the chair of virtual product development at Technical University of Dresden. His research area is in the field of architectured materials with focus on design methods and metallic microlattices. And in addition to mechanical engineering in general, medical engineering, with a focus to design improvement of bone replacing implants, for example, like knee, hip, or spine. And he is going to present the paper number 5 on proposal for load adaptive design of microlattice structures suitable for PBF-LB and manufacturing methods. Before we roll, I think we have a nice collection of different works. I would say papers 1, 2, 3, and 5 are somehow more similar, whereas paper number 4 is focused on a specific design involving AM. So, Philip, please, could you roll the presentations?
Hello, I'm Alan Eyre from the University of Strathclyde, and today I'll be presenting our paper entitled A Deformation Taxonomy of Additively Manufactured Lattice Structures. A brief introduction. Additive manufacturing offers opportunities for design mechanical deformation within parts by integrating lattice structures into their designs. The aim was to develop and expand on a novel taxonomy method that categorizes AM lattice structure deformation behaviors based on its strong parallels with mechanical motion. Today we'll discuss background on lattice structures, mechanical motion, and compliant mechanisms, cover the original taxonomy in previous work, and how this taxonomy has been developed and enhanced in this work. So what are lattice structures? In this work, lattice structures refer to the external form and tessellation pattern of an additively manufactured part's geometry. Lattice structures are forms that comprise of a small network of nodes, beams, and cells. This form creates a high strength to weight ratio, reduces material, and can help enhance a part's mechanical performance. Now, different lattices deform and behave in different ways, but if we can understand their behaviors, we can also predict and control them in our designs. This work utilizes 6 structure types, which can be seen in the bottom right, and each of the 52 variations were subjected to 5 mechanical tests. Deformation behaviors in these tests presented parallels with mechanical motion. In mechanics, there are 4 basic types of mechanical motion: linear, oscillation, reciprocation, and rotary. Now, all these motions present parallels with lattice structure deformations. Therefore, there is a value proposition for a novel classification method that uses these 4 motions to categorize the deformations. This method would suggest which lattices are suitable alternatives to multi-part assemblies and would aid in the design of compliant mechanisms. Compliant mechanisms are flexible mechanisms that create motion through elastic body deformation. They're designed to replace rigid multi-part assemblies with a single flexible part. Compliant mechanisms can be hard to design, but understanding lattice deformation behaviors and creating a classification system would aid in their development. Lattice structures could be integrated into the design of compliant mechanisms, replacing rigid parts with flexible controlled deformations. To the right, we can see a basic example of this theory in practice: a spring check valve redesigned to replace the reciprocation spring with a lattice structure, reducing the number of parts. The original taxonomy uses only the 4 basic motions. However, during a data reanalysis, an issue was found within rotary motion. 2 variations of this motion were identified with no method of separating them despite clear distinctions. These were lattices suitable for rotations greater than 360 degrees, but not less than 360 degrees, and vice versa. These findings uncovered a need to enhance the taxonomy motion themes further through the development of sub-motion themes. The rotary motion theme was initially expanded into 2 sub-motions: rotations more than or equal to 360 degrees, and rotations less than 360 degrees. These submotions were then expanded further through continuous and repeatability to indicate singular and dual directions of the rotation. Oscillation is challenging to identify in lattices. Typical oscillation motions are not directly attached to their pivot point. However, oscillation motion is also present in flexure, a motion involving a structure being bent between its pivot point and an end point. Results in MT5 show this motion is possible through lattices. Therefore, oscillation can be divided into 2 submotions: flexure and pendular. Reciprocation motion was expanded into 3 submotions: compressive, balanced, and tensile. Yield strength values in tensile and compression tests for reciprocation motion are typically mirrored, i.e. 100 newtons versus negative 100 newtons. However, some applications prefer an imbalance, either biased towards a greater compression or tensility. Therefore, it was important that this preference be reflected in the submotions. Linear categorization depends on whether a lattice is more suited to compression or tensile forces. It is noteworthy that lattices may be suitable for both and overlap with reciprocating themes. As such, linear categories share some similarities with reciprocation motion. Thus, linear lattices can be subcategorized as compressive linear and tensile linear. And here we have the final taxonomy with submotions included. A simple translation of an AM lattice deformation and motion taxonomy is crucial in its usefulness to designers and engineers, indicating what motion each lattice can replicate. An ideal method of doing this is through a visual illustration in the form of a dendrogram. It facilitates a breakdown of the behaviors, properties, and characterization of the lattice structures available. This illustration augments the original taxonomy to produce an enhanced dendrogram for AM lattice structure deformation and motion types, including submotions. For this work in 2D tessellation patterns, only areas relevant have been expanded on thus far. These are prismatic, planar, and periodic tessellation categories. In addition, there has been a change to the color coding used to create greater clarity. Sections are now deciphered using the colored lines above the dendrogram. The headers correspond directly with the sections below. The yellow section details the key underlying concepts that describe each structure's tessellation type and how these geometries are arranged and constructed. The green section highlights suitable motion and submotion themes for each lattice. Lattices may be deemed suitable for more than one motion type, depending on experimental results. This helps identify more adaptable samples and does not signal any drawbacks within a sample, should it qualify for multiple types. The most adaptable structures thus far in experiments are sinusoidal and kagome. In summary, the aim of this work was to augment a novel taxonomy we'd previously developed. The taxonomy in this paper presents a unique approach to lattice structure classification in additive manufacturing. It links the deformation behaviors of lattices to the 4 basic types of mechanical motion, which expand into 13 sub-motions. This method will enable users to find ideal structures for the development of AM-compliant mechanisms by integrating suitable lattices into their designs. AM and compliant mechanisms are both becoming increasingly prevalent in engineering. However, there is still a need for a process to incorporate controlled lattice deformation into a DFAM framework. Our taxonomy and database are key to this. Thank you once again to you all for listening, and I'll be happy to take any questions on the paper.
Hello, my name is Fiona Schulte from Darmstadt University of Technology. Welcome to my presentation on the influences and effects on scaling the pressure stiffness of additively manufactured mesostructures. Mesostructures are used in volumetric components like the shown crash helmet or the foot prosthesis to realize certain product functions. In the 2 examples, the potentials of separation of properties of the outer shape and the inner properties, as well as the grading of local properties according to requirements, are utilized. Mesostructures consist of regular structures with repeated elementary cells on the mesoscale. These determinate inner structures become manufacturable using additive manufacturing technologies. The properties of different mesostructures are investigated in finite element analysis or experiments. Yet dimensioning of the structures for applications is realized by the iteration of simulations, usually using equivalent homogenized properties. The iteration, though, is time-consuming. Hence, systematic and purposeful design requires a mathematical description of the interrelation between the design parameters of a mesostructure's elementary cell, the length, height, and width of the elementary cell's envelope and the structural thickness, and the mesostructure's properties. Therefore, a model for this interrelation is aspired. The mesostructure's stiffness properties are identified using a finite element method simulation model. As an exemplary load case, uniaxial pressure is examined here. To simulate the pressure stiffness of a mesostructure, a single elementary cell is modeled between 2 rigid plates with frictionless contact conditions. The lower plate is fixed, while the upper plate is impinged with a displacement in vertical, so that direction, and the response force in the reference point is output. To take the interaction of cells within a mesostructure compound into account, periodic boundary conditions are applied. These boundary conditions set the displacement of opposite nodes within the FEM mesh to be the same, like the elementary cell borders to another identical cell. The FEM simulations do output the overall stiffness, but provide little information about the contribution to the stiffness of the different geometrical features within the elementary cell. Thus, an analytical model for the pressure stiffness is derived from known mechanical interrelations and their description, supplemented with expected effects of the elementary cell's geometry. The analytical model of a face-centered cubic cell is shown here. To reduce the 3-dimensional geometry to 2 dimensions, the struts of the upper and lower respectively surface are projected to one plane. Now 1/8 of the cell is considered, while forces and stiffnesses are portioned or added respectively to achieve the overall stiffness of the cell. The force path through the FCC cell can be split into 2 parallel paths. The first path is modeled as a framework consisting of bars and showing a deflection depending on the tensile compression stiffness of the framework. The second path is modeled as a bending beam following the bending line with a double-sided clamping, additionally considering shear because the struts are stocky, and a compression arising through the hindrance of deflection at the knot. Furthermore, the knot areas correspond to a soft clamping instead of a fixed clamping, which is regarded in the bending line, which are considered here by an additional deflection. The partial stiffnesses of both load paths are summed up to the total compression stiffness of the cell. To provide a model for the calculation of the properties depending on the design parameters, structural thickness D and edge length L of the envelope, the result of the FEM and the analytical model are fitted with different approximation equations. Regarding the accordance of the fit function and the results and the physical background, the power function is chosen to be suitable. The power function is advantageous in terms of its reversibility, which allows to derive backwards the design parameters for a certain stiffness. Comparing the FEM and the analytical results of the overall as well as the partial stiffnesses reveals that for little D2L ratios, the framework's tensile compression stiffness is dominant, while for high D2L ratios, the bending stiffness increases more strongly and dominates the curve slope. Considering the different dominating underlying stresses for the stiffness, the approximation equation is subdivided into 3 parts, which show even closer agreement with the FEM results within their particular areas, as shown in the graph here. Summing up, for the systematic and purposeful dimensioning of mesostructures, a model for describing the relation between the design parameters and the mechanical stiffness is aspired. This is achieved by a power function approximation that describes the stiffness depending on the relation of the strut thickness to the edge length of the cell. The comparison of the approximated FEM results and an analytical calculation account for the identification of effects of geometrical features on the stiffness and the deduction of a matched 3-part power function approximation. The model shall be transferred to further load cases like shear, bending, or torsion, and for other elementary cells, which could be, e.g., cells with different edge length relations, and further cell types like plate or shell lattices. For complete dimensioning, furthermore, the strength and buckling resistance have to be modeled. Thank you.
Hello, I'm Didunoluwa, and I'll be presenting our paper, Surface Roughness and Design for Additive Manufacturing, a Design Artifact Investigation. Our paper focuses on the metal additive manufacturing technology, laser powder bed fusion. LPBF is an AM technology that uses a laser beam to melt powdered metal material to form parts layer by layer. Material is rolled onto the build plate within the powder bed, and the laser forms the part layer. Once formed, the build plate is lowered 1 layer thickness, and the process is repeated. LPBF is of high interest in industries such as aerospace, as the laser's position brings a high degree of design freedom, enabling production of near-net shape, innovative, weight-saving parts. For example, satellite maker Optisys used LPBF to enable a 100-to-1 part consolidating design for a metal microantenna, achieving a 95% weight reduction. Consolidated AM parts can be complex, often requiring support structure. However, for designs with closed internal sections, support cannot be included due to being impossible to remove post-build. These unsupported areas cause the melt pool to sink into the powder bed, and unsolidified powder leads to rough surfaces and dross formation, causing deviations from the part geometry. Additionally, without supports, transversal shrinkage occurs, as when 2 separately built islands meet, the residual stresses at their junction layer pulls the material together, and like dross formation, cause rough surfaces and geometric deviations from the part design, hence intrinsically linking rough surfaces to design choices. Literature indicates that these surface roughness defects have a negative impact on fatigue performance. Consequently, the benefits of part consolidation could compromise material properties, meaning there lies an intrinsic material-machine geometry relationship of parts made through LPBF. While post-processing is a common method of surface improvement, consolidated parts can make this difficult due to areas being inaccessible by design. Also, there are a variety of methods with different levels of effectiveness and varying costs. Thus, there is a need to develop design for AM supports that provide an understanding of design's relationship to surface condition and resultant material properties. Therefore, our paper presents the industrial use of a DFAM process that uses product-specific AM design artifacts. The AMDA process is a systematic way to identify, explore, and decrease AM design uncertainties when inspiring, evolving, and validating AM design solutions. Here we present an evaluation of results and the design logic through 2 iterations of the AMDA process, as it is used to investigate uncertainties related to surface roughness during the design of a rocket engine turbine manifold with a consolidated design. As it is not possible to remove support structure from the turbine's internal gas pipe, a series of design artifacts were first made to evolve possible unsupported roof designs. Once a roof design solution was chosen, there was the uncertainty of the impact of design-related surface roughness on the mechanical properties of this roof section. Hence, to validate the roof design, an artifact was designed to be fatigue tested to investigate this feature. This artifact, Artefact A, was designed to resemble the internal roof geometry of the manifold design, investigating the roof radius at a 4 mm radius, R1, and comparing it to a less rough surface of the same radius, the reference surface, R2, to the right. Shown in Figure A, R1 had a high level of dross formation, creating a much rougher surface compared to that of R2. Also, transversal shrinkage has occurred, indicated by a distortion line at the roof junction layer. 10 A artifacts were produced, and we found that the average R1 radius was 2.7 mm instead of 4, whereas the average for R2 was 3.9. Additionally, shown in Figure A right, where the artifact arm design changes from the R2 radius to an unsupported 45-degree overhang surface, a transition line from smooth to rough surface was noted, causing the point of fatigue failure at R2 to occur off-axis, as shown in Figure B right. To account for these unexpected failure behaviors, a second iteration, Artefact B, was designed with two major design changes to better focus the artifact on the studied uncertainty. Firstly, a tilt was introduced to counteract the impact of the transversal shrinkage and reduce the dross formation at R1. With a tilt, the R1 junction plane gradually connects over several layers, reducing the impact of thermal stresses as these layers cool. Additionally, Artefact B's square geometry should address the R2 off-radius failure due to the transition roughness by causing the failure to occur where the arm thickness is smallest. The A artifact aimed to validate the understanding of the design roughness fatigue relationship for a 4 mm roof section. Instead, it identified previously unknown process characteristics that impact the artifact design. Hence, the A artifact evolved our understanding of the AM process and led to the design of the B artifact as we aim for a more accurate representation of the design uncertainty under investigation. In this case study, the AMDA process has supported the detailed design through providing understanding of process characteristics impact on design whilst investigating a design consideration. In each iteration of the AMDA process, a new design artifact is built, which once tested, either exposes an unknown uncertainty and evolves the design understanding or reduces uncertainty through design validation. Each iteration of the AMDA process reduces the number of uncertainties while the designer obtains a better idea of the AM process and how to evolve the chosen design to account for the design uncertainties. Generally, come the final artifact iteration, the designer has reduced uncertainties and is provided with a clear understanding of design's effects. Thus, ideally, a design specification with no remaining uncertainties can be made that enables the validation of a final design solution. The AMDA process in practice has highlighted design issues that need to be considered when designing metal AM parts with closed internal sections. When designing the first artifact, a designer uses their current AM knowledge to focus the artifact on the main design uncertainty. Consequently, their level of AM knowledge will impact how fundamental the uncertainties are that need investigation. Our future work will focus on evaluating the B artifact design changes enable the verification of the design roughness fatigue relationship. Also, the B artifacts will have two designs, one to test the as-built surface and a second to test a machine surface, investigating microstructural fatigue performance design factors. Additionally, work should focus on developing the AMDA process for generic uncertainties, providing design engineers with support when exploring the capabilities of AM. Thank you for listening.
Ladies and gentlemen, together with my colleagues Oskar Martinsson and Axel Nordin, we conducted research on compounding and extrusion of composites directly on 3D printer. My name is Jože. We are coming from Lund University, Sweden, from Product Development Division. Additive manufacturing encourages design creativity and makes access to machining facilities affordable. A 3D printer, which enables extrusion and printing composites directly from the raw materials, was designed, assembled, and tested. The materials used in 3D printers based on extrusion are most commonly in a filament form, and it costs between 15 and 30 euros per kilogram. It can be cost limitation in many cases. Pellets or even recycled plastics are significantly more affordable. There are already some interesting commercial solutions, such as Direct 3D. Our research question was, can we produce well-homogenized composites in a scaled-down extruder? The following steps were used during our research: define, measure, analyze, improve, and control. The steps were repeated in several iterations. The goal was confirmation of research hypothesis with a practical experiment. Therefore, several versions of extruder were designed and tested. The screw design has a significant impact on the dispersion of the additive throughout the matrix. On one hand, twin screw design assure better material mixing. On the other hand, we wanted to keep the design simple. The extruder was developed in several iterations. A modular design was used. Parts were created and assembled in different combinations. Heat and wear resistance of materials were considered too. At the end, the decision was taken to use the single screw extruder design due to space constraints and promising test results. We installed two 40 watts heating elements. The casing was covered with a thermal insulation shield, which limited the heat radiation and helped to stabilize the temperature. Finite element method simulation were made with the goal to understand better the dispersion of heat through the assembly. Parts made from stainless steel were compared with aluminum one. Tests with pure PLA pellets were performed with variation of extruding parameters, screw rotational speed, and the composite temperature. We conducted two-factor design of experiments. The results show the relations between parameters and yield strength. The optimal parameters values were later used at making test samples. The material selected for the matrix was PLA, which is well suited for additive manufacturing. It is biodegradable too. The additive material used are the well-austenite fiber and powder of aluminum. Well-austenite has potential in replacing more expensive reinforced fillers such as glass fibers due to low cost and needle-like structure. Well-austenite increases tensile strength by up to 30%. Aluminum alloy powder with 10% of silicon was used as the second additive. The samples were analyzed with a scanning electron microscope. The image shows presence of elements. If we compare mapping, we can see calcium and silicon are located in the black spots of carbon and oxygen. That means both groups of elements exclude each other. We have done elements mapping on different locations of samples, and they were evenly distributed. The results from the mechanical yield strength test can be seen on the diagram. On one hand, well-austenite improved yield strength for 22%. On the other hand, aluminium has minor impact on mechanical properties. What are our conclusions? Compounds can be well mixed in a scaled-down extruder. It was confirmed. The tested matrix and additives extrude and mix well. There's a plan to test several new combinations of metal powders, color pigments, and different bio-based reinforcements. Additional variation and improvements of the extruder screw design is planned too. That's it. Thank you very much for your attention.
Hello, my name is Alexander Seidler. I'm research assistant at the Technische Universität Dresden. And our research group investigates in cooperation with the Fraunhofer Institute for Machine Tools and Forming Technologies the process and manufacturing design of metallic microlattices fabricated with a laser-based powder bed fusion of metals, short PBF-LB on conventional machines. During this, a new PBF-LB manufacturing-friendly approach for stiffening microlattices was developed, which I will present today. So for several years, lattice structures have been a focus of structural and material research for lightweight constructions due to their high specific stiffness in relation to their low relative density. In addition, the stiffness of these structures can be easily manipulated to create specific structural responses. So therefore, several methods have already been developed. However, the fabrication of metallic microlattices with the PBF-LB process is very challenging. That is why the Technische Universität Dresden and the Fraunhofer have developed new exposure strategies. Unfortunately, the established approaches to stiffening lattices cannot be implemented on such systems due to the production constraints imposed by the new exposure strategies. Consequently, the research presented here is focused on developing a proposal for a manufacturing-friendly stiffening approach for microlattices. So there are several geometric and topological approaches for manipulating the stiffness of lattice structures. In the geometric approaches, parameters such as the beam diameter or the cell dimensions are manipulated based on pre-calculations as shown in the approaches of Bu and Zhu. In addition to these, there are also approaches to change the stiffness of the overall structure by combining and integrating different cell types in a lattice structure, as for example in Wang approach. Alternatively, there are approaches in which the cells are arranged in a particular way to affect the stiffness of the overall structure, such as the approach of Shah. However, these approaches presented here cannot be implemented with the PBF-LB process, since manufacturing boundary conditions explained in the following are violated in all of these approaches. So for a support structure-free production of microlattice, which is needed, only a beam orientation of more than 20 degrees skin-down angle can be manufactured. So stiffening approaches such as those according to Wang and Wu cannot be realized. In addition, microlattices cannot be produced with conventional contour hedge exposed strategies shown here, since numerical inaccuracies due to the mesh-based description in the scan strategies lead to uneven energy input in the printing process, which results in necking effects of the beam as well as strong powder adhesions. So as a result, new exposure strategies for the production of lattices with beam diameters in the micrometer range were developed. Thereby, during the slicing, the lattice beams are described with either a cross, a weighted cross, or a line exposure strategy, depending on the beam diameter. With these strategies, a uniform energy input is realized, resulting in more uniformly shaped beams with lower powder adhesion. However, such good qualities can only be realized for uniformly thick beams, which means that also approaches such as Zhu's approach cannot be realized with this manufacturing technology. That is why a new proposal for stiffening microlattices under the mentioned condition is needed. So based on the above manufacturing conditions, a new cell design was developed. Therefore, the basis cell shown here is supported by additional self-similar subcells of smaller dimension, which relieves the beams of the basic cell and distributes the load over the entire structure. To evaluate the influence of the additional subcells on the stiffness behavior of the overall structure, numerical simulations were used. Therefore, a uniaxial compression test was simulated. For this, the cell was fixated at the bottom and loaded on the top with a displacement of 0.1 millimeters. The required force for the deformation of each cell design is shown in the chart, and based on these, the compression stiffness was calculated. So, all in all, comparing the result of all self-similar cell designs with the base cell, the stiffness increased by 49% by inserting one subcell and by 64% inserting another cell. However, the relative density also increased with respect to the base cell by 14% inserting one subcell and by 17% inserting another cell. Therefore, considering the light-weight aspect, the change in the stiffness is put in relation to the change in relative density. So the resulting change in relative stiffness in relation to the base cell has increased by 31% by inserting one subcell and by 41% inserting another subcell. In addition to that, the proposal was checked for production friendliness on PBF-LB system. Therefore, a complex lattice was designed, and for slicing the structures, a cross-exposure strategy was used for the base cell shown in red. A weighted cross-exposure strategy was used for the first subcell shown in purple, and a line exposure strategy was used for the second subcell shown in green. As shown on the right, the successful printed structure. So all in all, in this study, a new method for stiffening metallic microlattices for PBF-LB systems was presented. In this context, initial numerical simulations have shown that the relative change in stiffness could be increased by 41%. In addition to that, the manufacturing friendliness of the design was demonstrated by the successful fabrication of a complex structure. So in future, the numerical investigations must be validated with uniaxial compression tests, and furthermore, based on the self-similar lattice design, the influence of further parameter variation, such as diameter or cross-sectional shape, should be investigated on the stiffness behavior of the overall structure. These were my references. Thank you very much for your attention.
Thank you for the presentations, and thank you, Philip, for rolling the presentation. I suggest that we continue, I would say, as the order of appearance. So one by one, I saw lots of questions coming on chat, so I'm going to read the question per paper, and then maybe the author can answer. If there are too many questions, then I will try to make it even, right? Distributed. I will add some questions as well. And in the end, if you have time, maybe you can ask questions to each other, of course, if we have time. So I'll start with Alan and paper number 1, right? So there is a question from Serena Graziosi. It says, thank you for the very interesting work. Could you clarify how this taxonomy related to deformation, how this taxonomy related to deformation mechanism is correlated to the different lattice topologies?
Okay, you can hear me okay, yeah?
Yeah.
Okay. Okay, so during the initial experiments on the lattice samples, we identified some parallels in the deformations with that of mechanical motion, specifically in relation to the mechanical test that we were performing in compression, tension, and shear strength, which were done both in planar and non-planar. We noticed that the different lattices obviously performed differently to when exposed to the same tests. And at this point, we realized that predicting the behaviors of the structures would have implications in designing sort of mechanical deformation in single part prints. And this could, in effect, replace multi-part mechanisms. I think does that answer the question?
We will find out soon. Maybe, let's see what, yes. So Serena says yes. And then I proceed. I'll try, I have to go up and down constantly on the chat. So if I miss something, we'll come back to it again. So there is a question from Jože saying, thank you for the interesting presentation. So he would like to ask if the lattice geometry has a dominant impact on motion. I think which is a good question, right? So what's the correlation? And what about use of different materials and if lattice is produced with different AM processes? So how would you validate the model then?
Okay, so in terms of the dominant impact, I guess the answer is one of these typical ones that we seem to hear a lot of, but it depends. They all behave very differently, so it's hard to select a dominant sort of impact. But I think if I was to pick one, it would be along the lines of the Kagome and the sinusoidal lattices that were tested. They tend to be quite adaptable, but very responsive to reciprocation movement, which we believe is in part due to the spare material that it has, whether curved or polygonal, between the nodes in reference to the beam. So because it has spare material, i.e. in the curve or in a sort of triangle without connecting to another part of the lattice, it has a sort of predetermined deformation, which is quite easy to have. If I was to pick one. In terms of was it materials?
And the second one, what about use of different materials and if lattice is produced with different AM processes? So what happens to the model then?
Yeah, so although we understand that different process parameters sort of additive manufacturing, including materials and whatnot, will produce a lot of different variables. We were sort of aiming to understand the deformations of the external forms of the lattice structures themselves. So in the experiments, we took a lot of care to make sure that each test sample was produced under the same conditions, the same printers, the same materials, the same settings, to make sure that the only distinction between each sample was the actual tessellation pattern. The materials, of course, will have an impact, but it's something we're planning to sort of test further down the line at this time.
Okay, thank you. Jože, did that answer your questions? Yeah, he says thank you. Maybe I can ask several. I think we have time. So you said in the end, you are aiming to use your work for design, among other applications, compliant mechanisms, right? So the question is, why compliant mechanisms? Why not something else? Right?
Good question. Yeah, I think it was just the natural trajectory of the work. It was almost like sort of just uncovering things as we went along and realized that there was a lot of connections between what we were trying to do. The initial element was sort of trying to reverse this this general understanding that anisotropy is a negative thing in additive manufacturing, and trying to say that basically we can use these lattice structures to create a controlled anisotropy that allows us to have this designed mechanical deformation, and to us the obvious application of that was, as soon as we made the links with mechanical motion, was to see if we could create a method of some sorts that would allow mechanical mechanisms, compliant mechanisms to be sort of designed using this technique.
If I just may build further from that, right? It's a trick question that I ask because I have something in mind. When I was reading your paper before the session, and also listening to you present, I mean, you're talking about motion, right? And motion is, I would say, beyond large displacement, right? In a sense of elastic effects that you stretch something, right? And when you discuss motion, as you have shown it as a type of catalog or assistance for a designer, taxonomy, I mean, why not consider applications, for example, like in 4D printing, right? Or, when you have actually motion happening there, right? I'm also talking this in view of a recent paper from Martinsson that did something similar to you. They categorize different motion types for development of 4D printed structures. It really makes sense to talk about motion, or the research that I'm doing in origami, right? Where you have actually rigid body mechanisms, theoretically, right? And then you have a large motion, not displacements in effect of displacement, because I'm also worried, because if I would look in the area of compliant mechanisms, a lot has been done there, right? because you can design them easily using optimization, right? So people tend to move to, for example, shape morphing or other type of applications where actually your taxonomy would have a higher impact, in my opinion. Any comments on that?
Yeah, so in terms of the impact for the compliant mechanisms element, we kind of see this as developing a form of a standardization of compliant mechanism design. You obviously have a lot of stuff regarding these algorithms that can generate organic compliant mechanisms and things like that, but there's a bit of a disconnect between our understanding of how those compliant mechanisms actually work. And also, you know, on the other end of the spectrum, you've got these pre-designed compliant mechanisms that you can't really tailor or customize to your own design preferences or what it is you're trying to design in a part or a product. So we feel there's a gap in that area that we can look to exploit with this kind of research. And elements of, you know, when you look at these lattice structure deformations and all of these things, there's a number of different areas that you could expand into. This just happens to be the one that we've decided to investigate.
Thank you. We need to move on because I will spend too much time on you. So if you come back. So let's move to Fiona. So there is a question from Serena Graziosi saying, thank you for the interesting work. So question to Fiona, are you planning to consider in your model also defects related to printing processes or printing process?
Okay, thank you for the question, Serena. So I'm not going to actually consider those in the model yet, but I think you're right. It would be an interesting extension to my model to actually also consider those defects. What I'm going to do my further research is to, well, I initially evaluated my FEM model already to like prove that what I find out using my model suits what could be printed actually. So I've been using an SLM process, and I figured out for very little thicknesses of the struts, it's not too suitable because the FEM model over provides a higher stiffness compared to what actually can be printed due to the effects, which might also be related to the printing parameters I chose. So I think that would be an interesting further work, but I might not be able to do this in my one. Does it answer your question?
Yes, it is. Thank you very much. Thank you very much.
Thank you, Serena, for joining.
Thank you. Yes, thank you.
It's easier. Let me see. Are there any other questions for Fiona? If then maybe I can ask one, right? So thank you for your presentation. I was reading your paper before, and you asked the question, which influences and effects determine the properties of mesostructure elementary cells, which is a difficult one. And I just can clarify, you know, because you are doing something in your work, right? But if you take unit cells that are smaller, right, micro to nano, right, they behave as materials. So it's something different. The response is completely different in comparison to the response of macro structures like bridges that are also cellular structures, right? And they have, again, different response depending on the load cases and boundary conditions. And boundary conditions become really influential. So for your work, you know, you are focused on unit cells, yeah, and you're on the mesoscale. So that's the worst. You have the effects from below and effects from above, right? So my question is, why isn't it risky to just focus on one unit cell when you have a structure that actually depends on first how the unit cells looks like, right? Because they're not uniform. And B, how the boundary conditions look like, right? Because this is not the case of infinite structure, right? That you also talk about in your work that's homogenized, right? And you have something in between. So can you do such research that you can actually, with a certainty, say if you use this unit cell in design of your, you know, engine block or something that's very finite and it's not a material, it's not a structure, can actually produce good results? That's my question.
Well, so thank you. For the work in this paper, I actually just looked at like a uniform compound of elementary cells, but in my future research, I'm also going to look into gradient cells. As you mentioned, it's interesting for the boundary areas where maybe a closed skin is added to my volumetric part. And then, of course, I have to ensure that there doesn't come up a stiffness, like a skipping and stiffness, and then it's going to break, especially in this area. So I think gradient cells could be a solution for this problem. But of course, the properties change in case the cell is graded, and that's what I'm going to investigate in my future research. For this paper, I focus on the homogeneous cell compounds to first figure out what affects the simple elementary cell with no gradient and so on. Do you have, and maybe if it's possible to use those influences, like I have a knot area where if I have more of those, the cell becomes stiffer, and if the struts become thicker, of course this influence is higher, and thus I wanted to investigate this one first before I go to gradient structures, which would enable to also get a transition to maybe full material part areas of the part, or boundary areas.
Thank you. I think you need to take consideration of the whole. You have to be broad and specific at the same time, which is difficult, right? That's the Meso scale. That's the challenge there, right? So because you have boundary conditions and you have unit cells, which geometry changes, right? Although the topology is the same, the volume might not be the same, right? Because you have conformally mapped it, and then you have an issue. Because the properties, the mechanical behavior of that unit cell has nothing to do with the ideal unit cell, right? Thank you. Interesting work. We have to move on to paper. If we have time, we come back to you. To paper number 3. And there are some questions there from Serena saying, great work. Are you planning to exploit these results into a model?
So currently, no. The main reason for that is because we needed considerably more data, because for this particular AMDA process, we were searching a specific uncertainty within the design of a rocket engine turbine component. Also, we were using a very specific set of parameters for the manufacturing of these artifacts, meaning that if one wanted to make a model of this, you'd need to model it a considerable number of times under different parameter sets, and therefore it would be, I would love to have a model of it, because at the end of the day, one thing we did find from our research that the future of surface roughness understanding will be in modeling, rather than this effort that we've done is quite time consuming now, but the hope is that over the years, as more and more knowledge and science is brought about it, models of this surface roughness phenomenon will be able to make, that will enable designers to have a much easier process of understanding how their surface roughness will impact their design, because there's so many different aspects. There's the design of it, there's the level of surface roughness, there's the interaction of that surface roughness with the material properties, and future work we've looked at is looking at, again, the material microstructure and how that's influenced by the amount of surface roughness that's left on there. So yes, I would love to have modeling, but right now my scope is way too small to be able to conduct that.
Thank you.
Thank you. There is another question from you, from Jože, saying, thank you for the interesting research. How universal are your validation conclusions? And is it possible to transfer conclusions to different AM machine manufacturer or even different AM technology?
So I'll take that step by step. So universally, in terms of the conclusions that we have received through this specific AMDA process, it is very specific to powder bed fusion processes. So potentially EBM as a liquid polymer fusing powder bed processes. Yes, because we are specifically in this artifact process looking at the impact of surface roughness, and that surface roughness tends to be due to the powder bed process, because it is a characteristic of the process. So possibly not for this conclusion, probably not for other processes outside powder bed fusion, but other processes which use different heat sources than a laser, these conclusions could be very useful to those looking at these because of the characteristics that are shared between the powder bed fusion processes. And different AM machine manufacturers, definitely, because again, it is the characteristic of the process that is impacting given the uncertainty of the fatigue performance for this particular design, because our particular product that we are trying to overcome the design uncertainty of, we have chosen one particular machine, which is laser powder bed fusion, but any other laser powder bed fusion machine would have similar problems with our uncertainty in our design choices. But then again, with the different AM technologies, this AMDA process is really focused and honed. It is the process that we've utilized to solve or to find solutions for this design uncertainty. So you'd have to probably look at the issues of another process which may be similar to this issue, but then the MDA process will probably need to be repeated in order to find more appropriate conclusions than be able to directly translate what we have got to different AM technologies. Has that answered your question?
Yes, thank you.
Great.
Thank you.
May I ask one? We have time. So because I'm building further from Jože, and I ask also myself that, because he said that is it possible to transfer conclusions to different AM machine manufacturer, right? So the question is, in the future, right, are we going always to be somehow driven to a situation in which once you get a new machine, right, it doesn't have to be a new process, right, just a new machine. Are we always going to have to build a model that will actually account for the performance of a unique machine? Or we could have ideally a situation like we had in the last 100 years, right, with a conventional manufacturer, and they say, oh, this is the tolerance field, this is the surface roughness, I know where I am, right? Because, for example, in implant design, right, you have to certify certain machine. It's not only process, it's actual unit, right? Because two different units from the same manufacturer do not perform exactly the same. So what are your thoughts on that?
Well, I've encountered that exact in my experience within industry, where we did a lot of testing and qualification on one machine, ordered the exact same again, but there had been an update, and therefore there was a big problem of, are we able to both qualify the process or also qualify the machine? But then the changes in what has happened, because you need to qualify the part, the process, and the machine for these to be able to say that our results from previous are comparable to our current results. My hope is that one day we'll be able to have some form of something that is able to compare the differences between these machines that can conclude that results from taken previously would be it. Well, right now it is a big discussion within the industry of, can we do that? How do we do that? And yeah, because right now I understand that we would definitely have to repeat the process again, but because we're trying to focus on very, very exact results. So our fatigue numbers may be different in a different machine, but the understanding of the characteristics should remain the same. And that is part of what this AMD process is. We've learned about the AM process and its characteristics and how they influence design, rather than just the results of the fatigue results. The fatigue results will come out in a different paper, but for the research we've done here, it's more about how is the process impacting our design choices, and what is the impact of that, and then how do we mitigate for those negative impacts, and or how do we create a tolerance level that we know that if we have this particular design, it's going to be this level of roughness, which is going to lead to this level of fatigue performance. That's the long-term aim, and be able to get all this information into a guideline is our overall aim as well.
Thank you. I mean, we experience this in research, right? What colleagues are doing every time you get a new batch of material for your research, first you characterize, because you don't know what's new, right? Otherwise you can't build on previous results. Okay, thank you. Great work. Let's move further to Jože and paper number 4. There is a question from Serena Graziosi to Jože Tavčar saying, very interesting. Have you compared the mechanical properties you obtained with the one of similar composite filaments? So is there a comparison of the results?
So unfortunately, we started to use a bit unusual additives, unusual composites, and they are not at least according to our knowledge, they are not commercially available. But definitely it has definitely will be the next steps also to directly compare. So what are the results with the so-called professional composition of filaments and use them on 3D machine, and this direct extrusion of composites on 3D machine. Maybe I would like to explain the context of this research. So actually, if we are doing so-called online extrusion, we are against some principles. So definitely, it should be better if we do extrusion on and compounding on the specialized machine. This is somehow kind of improvisation, but in the context that about the democratization of this 3D printing possibilities, it's if we want to play with different composites, different combinations, also in the areas where not top-level technology or facilities are available and where the costs are important, then such approach is interesting.
If I may add, Tino, one comment.
Yeah.
Yes, of course, it's very interesting. For example, I was thinking about the possibility, thanks to the approach we are using, to use this kind of solution for large format additive manufacturing, because starting from pellet, okay, as you did as well. So again, congratulations for your work.
Yes, it can be, the difference in costs can be 10 times if we use filaments or pellets.
I have another question popping up from Didun, asking, what are some of the other combinations that you wish to test?
So as I said, one is one point is to reduce costs. So even if we use so standard combination like the glass fibers, it's also interesting. So to make this available for much lower costs, and then some more also exotic material. So we don't have so exact plans, but so this principle actually, first we wanted to open the possibilities, to really to try many different options, and we think that if there will be many trials, there will be also some interesting combinations. For example, in the last years, I was working a lot with the polymer gears, and it can be one interesting continuation of research. While polymer gears are there are different load levels, such as temperature, wear, and fatigue load. And for example, by testing, we have found out that some combinations that are sell as very perfect, for example, with very costly material, was at the end worse than the basic materials, while there were no fatigue. So especially, yes, for some specific research areas like polymer gears, we would like to try different combinations that are not available by commercial available compounds.
Thank you. Does this answer a question? Cool. Okay, I'll not ask my question now. I'll move on because we will run out of time. So let's go to Alexander, and there is question again from Dylan asking, what is the impact on building times, material usage, and component weight with the increases in stiffness? Would one have to make trade-offs for increased stiffness?
So yeah, thank you for the question. I would say the biggest trade-off is the building time, because if you increase the stiffness with including more subcells to increase the stiffness, the building times and slicing will increase, and as much as the files you need to import in the machines. So the biggest trade-off is the building time. And furthermore, if we add more subsets, the weight is increasing, but not as much as the stiffness. So yeah, the biggest trade-off is at the moment the building time.
Okay. Let me just check the check. Does this answer a question? Yeah, cool. I have a question. Just a second. Thank you for the presentation, Alexander. I have a question. So when you show your approach, right? You basically, and I also built on what Didun has asked, because I think this is a really good question, because he asked what do you get weight with respect to stiffness, right? And the thing is, you have compression tests, right, in your work, right? And what you do, you actually take a length of a bar and you cut it in half, right? So you have actually half the buckling length, which is great, right, for compression test and compression load cases, right? And you gain a lot by doing that. And if you look, for example, the transmission towers around that carry electricity, this is exactly how they are designed. There is always a buckling length cut in half. Now, my question is, what happens if you change the load conditions, right? Because the thing what Didun has asked is that you will lose on utility, right? Because you can gain a lot if you assume compression, and you would, even if you would optimize, you would gain a lot by subdividing there and actually cutting the buckling in half. But otherwise, no, right? So why would this strategy work better with respect to a generic optimization, right? For example, that could easily calculate the optimized design for multiple load cases rather than just compression. So somehow, if you can comment on these things.
Yeah. So this proposal is not fancy at all. So there are a bunch of fancy approaches in cell design and structure design. But the biggest problem is what we are facing is we want to implement or to provide micro lattices on conventional machines, and therefore we get boundary conditions in the manufacturing. And this is why there are problems with the skin down angel, where the generative design or topology optimizations produces cells which are violated these conditions, and therefore we would need support structures in microlattices, which is not possible because our microlattices are in the scale of the support structure. And therefore, we wanted to make a proposal for a design which is support structure free and can be manufactured in the range of the laser focus diameter of common machines.
Mm-hmm. But then you could, you could say something else. You could say, for example, that you are making some kind of a generative system, not the sense of a generative system of a topology optimization using density methods, but in true sense of generative system. And actually, you have some kind of design rules that actually subdivide the space such that always the certain overhang angle would be obeyed there. So you can actually print without any support structures. You can do something like that, for example. Then it will become more fancy. That's definitely the case.
Yeah. Maybe.
Okay. Let me just see. We have I think 5 minutes left. Do you guys have questions for each other, maybe? No. Then I will have one question for Jože, if I may. So thank you for your work, Jože. I was, just a meta level question. So you developed an extruder, but I think there are many applications in 3D printing that benefit from extruder, and I think Serena also mentioned that, right? If you go to macro scale, for instance, you have cement or you print food, right? Or also sustainability aspects that you mentioned. Are there any specific lessons learned that are generic to design of extruders regarding additive manufacturing, and could you actually make a design method for that? Because I think that many applications will come in the future regarding that particular device.
So maybe an interesting information. We were using this machine that has possibilities for modular building. So it was, how to say, relatively easy to upgrade this machine. And one running project is of printing food.
Of course.
The tests were done on exactly the same machine with some additional adaptation. So this printing food is used for elderly people. So so if you have bad teeth and you have difficulties what kind of food you can get, but it's annoying if it's just so how the outlook of the food is bad. But printing food, you can make it more attractive. So even
of course, it's a viable cause, definitely, right? Yeah.
Of course, it make additional problems how to clean everything, how to make. But it's, for example, an interesting on running project.
So there are commonalities, right, between current extruder and other applications as well, right?
Yes.
Yeah. Thank you. I think if there are no more questions, I think that we are done. I mean, so thank you all of the presenters. Thank you for their great work. Thank you for the audience that was very active, made my job much more easy. And thank you also to Philip for helping us with the session.
Thank you.
We are done. I'll do it live.
Thank you all.
Thank you.
Thank you.
See you guys.